Classification of particles. In this fourth elementary particle physics video, we will study how particles are classified and conservation laws. A study of particle interactions has revealed a number of new conservation laws, which, just like the old ones, are ordering principles. They help to explain why some reactions occur and others do not. Thanks in advance for watching this video. If you like this video, don't forget to like and subscribe to the channel and activate the bell. It is very important for the continuity of this channel. Over time, hundreds of subnuclear particles were discovered, and the first step in making sense of all these particles was to look for patterns, similarities, and differences so that particles could be classified into groups. One way to classify the particles is according to their interactions, since not all particles interact via all four of the forces known in nature, though all interact via gravity. The particles were arranged into three groups: hadrons, leptons, and exchange particles. The lepton group is made up of the electron, the muon, and the tau particles, and three different neutrinos, each of which is associated with a specific lepton: the electron neutrino, the muon neutrino, and the tau neutrino, and all their antiparticles. 12 particles in total. Leptons do not feel the strong force. The charged leptons have electromagnetic as well as weak interactions. The neutral ones only interact weakly. Leptons appear to be truly elementary point-like particles with no structure. Since there are three distinct types of neutrinos, each of which is associated with a specific lepton, when an interaction involves an electron, the electron neutrino appears. When it involves a muon, the muon neutrino appears. And when it involves the tau neutrino appears. For example, positive pi meson decay. A muon neutrino is always observed. It never results in an electron or tau neutrino. In the muon neutrino-neutron interaction appears a muon, never an electron or a tau. The positive muon decay produces a muon neutrino, a positron, and an electron neutrino. It never results in a tau neutrino. Some of the important properties of leptons are listed in the table below. The second group of particles is the hadrons, which are composed particles because they are made up of quarks and are therefore subject to strong nuclear force. Since hadrons interact via the strong nuclear force, they are said to be strongly interacting particles. They also interact via the other forces, but the strong force predominates at short distances. There are two subgroups of hadrons: baryons, which are particles made up of three quarks, and mesons, which are made up of a quark and an antiquark. Each baryon has its own antibaryon. The proton is the lighter baryon and the only stable baryon. The other baryons have masses greater than the proton mass, so all baryons, with the exception of the proton, decay in such a way that the end products include a proton. The proton and the neutron are well known and make up most of the mass of the universe. The more massive baryons are only observed at high energy inside particle accelerators, or as the result of interactions of cosmic rays with particles in the upper atmosphere. All mesons are unstable and are known to decay finally into electrons, positrons, neutrinos, and photons. Most mesons are high-energy particles and are only seen inside particle accelerators or as the result of interactions of cosmic ray with particles in the upper atmosphere. Some of the important properties of baryons and mesons are listed in the table below, but keep in mind there are many other baryons and mesons. Conservation laws. One of the maxims of nature, sometimes referred to as the totalitarian principle, is whatever the laws of nature allow must, in fact, exist or happen. For example, look at the following reaction. Even though charge, energy, and so on are conserved, this reaction has never been observed. If a conceivable decay or reaction does not occur, then there must be a reason. The reason is usually expressed in terms of a conservation law. To understand why this and other reactions do not occur, physicists have created new conservation laws. Three quantities are always conserved in any interaction. These are charge, momentum, and mass energy equivalence. To these, we add the quantum number conservation laws, lepton number, baryon number, and strangeness. These conservation laws are empirical discoveries. They have no theoretical foundation. They are supported by abundant empirical evidence. To explain the possible and the impossible reactions of the leptons, each is assigned a lepton quantum number, which must be conserved in a reaction. All the leptons have a lepton number equals +1. All the empty leptons, like the positron, have a lepton number equals -1. And all other non-leptonic particles have a lepton number equals 0. Look at the table on the left. The law of conservation of lepton number states that the total lepton number before an interaction must be equal to the total lepton number after the interaction or decay. In any particle interaction, the law of conservation of lepton number holds. To explain the possible and the impossible reactions of the baryons, each is assigned a baryon quantum number, which must be conserved in a reaction. All baryons have a baryon number equals +1. All the antibaryons have a baryon number equals -1. And non-baryonic particles have a baryon number equals 0. Look at the table on the left. Like lepton number, baryon number is also conserved in particle interactions. The law of conservation of baryon number states that the total baryon number before an interaction must be equal to the total baryon number after the interaction or decay. In any particle interaction, the law of conservation of baryon number holds. Before the third conservation law is stated, we must understand what strange particles are. Strange particles are those produced rapidly by strong interactions and only in pairs, and then decay slowly through weak interactions. Let's see one example when a positive pion interacts with a proton. Two neutron strange particles are produced, delta lambda and Ko, with high probability following the reaction. The lambda particle then decays through the weak nuclear interaction according to the reaction. And the kaon decays via the weak interaction according to the reaction. The search for the answer for this strange behavior led physicists to introduce a new quantity called strangeness. The strangeness numbers were arbitrarily chosen and for some particles are given in the table on the left. Whenever a nuclear reaction or decay occurs, the sum of the strangeness numbers before the process must be equal to the sum of the strangeness numbers after the process. In reactions or decays that occur via weak interaction, strangeness is not conserved. Finally, don't forget that relativistic calculations are needed to verify that energy is conserved in any reaction. However, we can make two observations. For two or more colliding particles, the reaction is energetically possible if sufficient kinetic energy is applied to the reaction. For particle decays, the conservation of energy requires that the mass of the decay products be less than or equal to the mass of the decaying particle. Determine whether the following reactions or decay can occur. The net charge is zero before and after the decay, so the charge is conserved. The baryon number is 1 before and after the decay, so the baryon number is conserved. There are no leptons in this decay, so there is no problem with the conservation of lepton number. This particle is a strange particle, and it decays via the weak interaction, so the strangeness is not conserved. The rest energy of the sigma plus is greater than the rest energy of the photon plus the rest energy of the pion. So the energy is conserved, with the resulting particles having kinetic energy. Therefore, this reaction can occur via weak interaction. The reaction is allowed. Let's see the next example. The net charge is zero before and after the decay, so the charge is conserved. The baryon number is 1 before and after the decay, so the baryon number is conserved. The lepton number is minus before and after the decay, so the lepton number is conserved. There are no strange particles in this reaction, so there is no problem with the conservation of the strangeness number. This reaction occurs if the neutrino energy is at least 1.8 mega electron volts. The reaction is allowed. Let's see another example. The net charge is zero before and after the decay, so the charge is conserved. The baryon number is 1 before and after the decay, so the baryon number is conserved. The lepton number is 0 before and minus 2 after the decay, so the lepton number is not conserved. There are no strange particles in this reaction, so there is no problem with the conservation of the strangeness number. The rest energy of the proton is less than the rest energy of the neutron plus the rest energy of the positron, so the energy is not conserved. Let's see another example. The net charge is zero before and after the decay, so the charge is conserved. The baryon number is 1 before and after the decay, so the baryon number is conserved. There are no leptons in this decay, so there is no problem with the conservation of lepton number. The strangeness is conserved as well. This reaction is energetically possible if sufficient kinetic energy is applied to the reaction. This reaction occurs if the meson energy is at least 1051 mega electron volts.